Before we do our next example, I want to just take a look at a very common way that we have of describing surfaces, which would be if we're looking at the graph of a function where z is a function of x and y. And of course, this could be modified if x is a function of y and z, or if y is a function of x and z. Again, I've got one of my three variables as a function of the other two. Okay. When I have that, a parametrization that I can use, and commonly will be to let x be u, y be v, and then z just becomes a function of u and v. Now in the last example, we didn't do that because our function involved a square root. And I know that when I take the partial derivatives, that same square root's going to show up in the denominator. And if I'm working over a region where the square root is ever going to be 0, that's going to give me something that's undefined. But very often we're going to have functions where the partial derivatives are not going to be undefined. And so this is a very convenient parametrization. What I want to do is just work through what our scaling factor is in switching from ds to dA. Okay. I know it's going to be the magnitude of del r del u crossed with del r del v, but this is such a common form of the parametrization that I might accidentally memorize the result, especially because we've actually seen it before. Okay? Now, if I take a look at the partial of r with respect to u, I'm going to get 1, 0, the partial of f with respect to u. Now notice that's the same formula as the partial of f with respect to x, it's just that I've done a name change. Instead of calling my first variable x, I'm now calling it u. But my parametrization has it so that x is u and y is v. So I've essentially just changed the names of those variables. Okay. Now if I look at the partial of r with respect to v, I'm going to get 0, 1, the partial of f with respect to v. Now these vectors should look familiar. Back when we looked at the surface area for the graph of a function, we determined that these were the vectors. We wrote them in terms of x and y at the time. These were the vectors that determined the parallelogram we would get in the tangent plane that lay above a rectangle in the xy plane. Okay. So when I take the cross product, del r del u, del r del v, that's going to be my symbolic determinant, ijk, 1, 0, partial f partial u, 0, 1, partial f partial v. All right, for the I component, I'm going to get nothing minus the partial of f with respect to u. For the j component, I'm going to get nothing minus the partial of f with respect to v. And for the k component, I'm going to get 1. Now, for our purposes in this section, I don't really care about this vector. I care about its magnitude. I will let you know in the next section, we're actually going to care about the vector itself, including its direction. Okay. So we'll see this again. Okay. But for now, if I'm taking the magnitude of that, del r del u crossed with del r del v, that's just going to be the square root of partial of f with respect to u squared plus the partial of f with respect to v squared plus 1. Now that should look very familiar because back when we were finding the surface area for the graph of a function where z was a function of x and y, we wrote this in terms of x and y, but that was exactly what we integrated. Okay. So this is what I will get as my scaling factor when I'm switching from ds to dA. Okay. It is totally fine if you want to write this out and derive it. In fact, I would recommend that you do that once a day for the next couple of days. If, as a result of that, you accidentally memorize the result, that is also totally fine. I am not recommending that you make flashcards and sit down and study them and really try hard to memorize this. I'm recommending that you understand where it comes from, and that way, if you should accidentally forget it after having accidentally memorized it, you can always get it back by deriving it. But I am fine if you are working with a surface that's described this way, and you can use this parametrization, and it doesn't give you an improper integral, I'm totally fine with you jumping to this result. And in fact, very often, when I do jump to that result, I don't bother to switch to U and V. If I'm going to write out the parametrization, I like to have my parameters named different things than the output variables, which are x, y, and z. But if I'm taking a shortcut and jumping right to that, then we're okay. So let's suppose that S is the portion of the paraboloid z equals 1 minus x squared minus y squared lying above the xy plane. Okay. And let's suppose I wanted to integrate over S. Oh, let's just integrate z with respect to surface area. Okay. Well, what I can do, if I want to, is I can say, z is a function of x and y. There are no square roots involved, so I'm not worried about getting square roots in the denominator and getting something that's undefined. So I could say here, if I call this f of xy, I can say, okay, I'm just going to get the double integral over d. Now d would be the projection of this shape onto the xy plane. And if it's this portion of this paraboloid that lies above the xy plane, that's just going to be the disk enclosed by the circle where this intersects the xy plane. Of course, this will intersect the xy plane when the z value is equal to 0, but that's when x squared plus y squared is equal to 1. So d here is just the unit disk. Now, I can rewrite my integrand in terms of my parameters. Now, if I'm using the parametrization that x is u and y is v, I would rewrite everything in terms of u and v. If I've accidentally memorized this result, it's okay to keep it in just the names x and y. Totally fine to switch to u and v, totally fine to keep it in terms of x and y. That was my original integrand. Then I'm going to get my scaling factor dA, and I know that my scaling factor is just going to be the square root of the partial of f with respect to x squared plus the partial of f with respect to y squared plus 1. Now, if this was my f of xy, the partial of f with respect to x is just negative 2x, and the partial of f with respect to y is just negative 2y. So I'm going to get the square root of, let's see, that's going to become 4x squared plus 4y squared plus 1. Okay, so this is what I would get if I wrote it out in terms of the parametrization, except I would have u's and v's. I'm just taking a shortcut here that I know that this, which is what I would integrate if I were just finding surface area, is the same as the scaling factor that I'm going to get if I'm integrating a surface integral. Okay, now at this point I probably want to switch to polar coordinates. If I had wanted to, I could have from the beginning used as my parametrization r and theta, so that x would be r cosine theta and y would be r sine theta, and then z would be 1 minus r squared. That would be totally fine. I chose to keep things in rectangular coordinates so I could use this shortcut that I had accidentally memorized, that the thing I would integrate for surface area is the same as the scaling factor when I evaluate a surface integral. But now I do want to switch to polar coordinates. So this is going to become, let's see, since we're integrating over the unit disk, we're going from 0 to 1 and 0 to 2 pi. That's going to become 1 minus r squared. This is the square root of 4r squared plus 1, and then dA is r dr d theta. Here, r and theta were not my original parameters. I'm switching from x's and y's to r's and thetas, so I've got another scaling factor so that I can switch from integrating dx dy to dr d theta. Okay. If I had parametrized originally with r and theta as my parameters, this factor of r would have shown up in the original scaling factor that allowed me to switch from ds to dA. Okay, let's see what this gives us. I've got the integral from 0 to 2 pi, the integral from 0 to 1. I'm going to distribute this r, and actually I'm going to distribute everything. So I'm going to get r root 4r squared plus 1 minus r cubed root 4r squared plus 1 dr d theta. Now, this looks like it's nicely set up for a u sub. This, at first glance, doesn't look like it is quite so much, so you might be tempted to do a trig sub. You could. There's nothing wrong with that. I will just remind you that if you do a trig sub, it is necessary that you tell me what interval your theta values can take on. Okay? That is an important part of doing the trig sub. So if I were doing a trig sub here, it would probably be that 2r would become tangent of theta. And when I'm working with tangent, theta is always in the interval from negative pi over 2 to pi over 2 in general. Okay. Now, oh, and I wouldn't actually want to use theta because we've already got a theta. So we'll say tangent of alpha. And alpha would be in this interval. Okay. If I want, I can use the fact that because I'm describing it in terms of r, I can actually find specific limits of integration. This would basically become inverse tangent of 0 to inverse tangent of 2. So with a definite integral, I'm going to have specific limits of integration. So you could either say this is the general thing that I'm doing for any trig substitution involving tangent, or you can find the specific limits of integration here. That is necessary because at some point you're going to be taking the square root of a trig function squared, and that's going to be the absolute value of the trig function. And if you don't know what interval of angles you're working with, you won't know whether you can drop the absolute value or not. Okay? So that is a necessary step that I am very particular about, but that some of you may have had a professor who's a little bit less particular about it, who may not have enforced that when you had 3B. So, you've been warned. Okay. However, that said, I'm not going to do a trig substitution. Because personally, I think trig substitution is just incredibly cool. I love the idea of trig substitution. But I find it incredibly tedious to actually do it. So, I usually will work pretty hard to avoid it. And it turns out the same u substitution that's going to work here is going to work here as well. Okay. So I'm going to do one u substitution. I'm just going to have to do a little bit of extra work to make it work in this particular case. We've been going for a little while here, so I'm going to stop this video and we'll finish up this example in the next one.